knowledge-based agents, and we said that how we represent an agent. It has a knowledge base, and then based on knowledge base, we have some kind of knowledge, and then we can make some decision. If, for example, we take a few examples that if it is raining, if it is Tuesday, then John go for a run. So if John is not going for a run, then it means that either it is not Tuesday or either it is not raining. So it means that based on certain knowledge base, we can train our agent, and then we can make certain decisions. That's why we say that in case of knowledge-based agents, we have a kind of knowledge base which is all the useful information about a certain application, and then based on that information, we try to train our agent, AI agent, and then we make certain kind of decision. So in this case, you can see that we have this knowledge base. For example, we have different sentences. We talk about sentences, that sentences, not English sentences, but any logical information about a word, about a problem is called a sentence. So if it did not rain, T didn't visit Brown today. Then it says that it can visit only one of them. And then finally it says that T didn't visit John today. So it means that if it visited John today, it cannot visit Brown. And at the same time, if it visited John today, it means that it's also raining. So then based on any knowledge base, we can make more, we can use more information. Then we talked about propositional logic, and we said that we have certain kind of sentences, and then based on those sentences, we can make different kind of connectives. For example, like I said, that if it is raining and something, if it is raining or something, so this P, Q, and R can be certain kind of sentence, and then based on these sentences, we can combine them to form a knowledge base. And once we have a knowledge base, then we can use them again to draw certain more conclusions. And why we need that? We need that so that based on certain information, we can infer something, so that our agent is trained in such a way that it can infer something about a certain environment. Then we also come to know that for propositional logic, we have these 5 operators. One is called not operator, which means that if P is true, not of P is false. It is raining. If it is raining, it means that not raining is false, and so on. Then we also came to know about and, or. In terms of and, we know that if both of them are true, or either of them. We also came about implication that if we say if a right hand side is true, then the left hand side is definitely true. If I say if this is happening implies that this is true, it means that if left hand side is true, right would always be true. Right. Then we talk about entailments, because like I said, that for any environment we'll be having certain information, but to use that information, it is very important that the agent has the capability to draw various sentences or various true entailments. Entailment means that any information that can be led from the given information. Like if in the previous case, you can see that there were 3 sentences that if Tyrion visited Brown today, there is no rain, then other, and then based on that, we made few entailments that if he is visiting John today, he cannot visit Brown today. So this was a new sentence, but it was a true entailment because it was coming from the knowledge base. And why entailment is important? Entailment is important because you have certain information in the knowledge base, and if there is some new information came in, for example, you were having certain information about Tyrion when he is visiting, and then an information came in that it is raining today. Then what you're going to do? You're going to check whether this is entailing your knowledge base. If yes, then you can make some argument. It means that then you can make some decision. But if, for example, if any information is not colliding, or if it is not true with respect to knowledge base, then it would be a wrong entailment, and then we cannot make a decision. So that's why it was very important to have entailments, and that's why AI agent look for all the possible entailments. For example, here in this case, This was our knowledge base. If it did not rain, Tyrion visited Bronn today. Then we move forward. Then AI used this knowledge to make further information. For example, Tyrion did not visit Bronn today. Why it has made this entailment? Because based on this information, where it says it visited Jon today, and based on this information, it says that okay, it can visit one of them, so it made a new entailment. And then we made another entailment that since Jon is visiting, Tyrion is visiting Jon today, cannot visit Bronn today, and when it is not visiting Bronn today, it is rare. So it means that it is very important to make entailments. Now, it is quite possible that you make an entailment, or in other words, what we are doing, based on certain sentences, we are inferring certain different scenarios. So I can make some scenario that, for example, here I say Tyrion did not visit Bronn today, and it is Sunday. So now this is an inference, but this is not entailed to knowledge base. So it means that it is possible to have inferences, but it is very important that the true inference should entail the knowledge base. This is only. So it means that from here we came to inference, because we want to train our neural network to make certain kind of inferences, but those inferences should be entailed with the knowledge base. Okay. So again, here you can see that we said it is raining, it is Tuesday, Jon will go for a run. Now, if we simply say inference, it is just making certain sentence. For example, I said it is raining, it is Tuesday, Jon will go for a run. So here R was an inference. But whether this inference belongs to knowledge base or not, we're going to check it with the model. From the model, I can see that yes, if it is raining, and so our model is telling that if it is raining and if it is not Tuesday, Jon will go for a run. So this is our model. So it means that it is raining, it is Tuesday, based on our model. So whatever inference we are making, we need to look at the model. So now I can see that it is raining. These were 3 sentences, and based on this model, I made a new inference. So now, if I did not knew the model, and if I say I make certain inference, then I need to check whether it is according to the knowledge base or not. For example, if it is raining, if it is not Tuesday, I could have said Jon will not go for a run. But if it is raining, if it is not Tuesday, Jon will not go for a run. Then it will not entail to the knowledge base. So it means that whatever inference we are making, it should be entailed. Now, there are 2 ways to check the entailments. One we have already studied. Okay, as I said that why inference is important, why entailment is important, so that we can train our AI algorithm with all the possible knowledge. But now, as I said, our goal is to decide whether KB entail A, or in other words, we read it as if sentence A is entailing KB, if any new sentence is based on the knowledge base. So the very first algorithm is, if you have certain information, try to draw all the possible models out of it. We will see it in a while. And we have already studied. So our first algorithm for inference is to draw all the models and then check which of the model is same as knowledge base. This is one of the methods. And then we have another method as well. So yeah, so this is the example. Here you can see that we are saying we have 3 cases. It is raining, it is not raining, it is not Tuesday, and Jon will not go for a run. Similarly, we can make all possible combinations. So it means that this is one model, this is second model, third model, fourth model, and so on. And it is same as if you look at knowledge base. So inside knowledge base, what is model inside knowledge base? It is if it is raining, because P is true, If it is not Tuesday, John will go for a run. So it means that out of all these models, we need to check it with the knowledge base. So which model do you think would be best? Because all of them are models, right? Because this is P naught, Q naught implies R naught. Does this belong to knowledge base? The very first line? No, right? Then again, if I go to the second one, again, P false, P naught, Q naught are true. Again, does it satisfy, right? The only possible case would be where P is true, P is true, Q is false, and R is true. So it means that this is the only knowledge which is consistent with the knowledge base. So this was one of the methods in which, based on certain scenarios, you create all the models and then keep on checking those models with the knowledge base. But this method can be hectic when we have, for example, if you have more sentences and if you have infinite sentences, then drawing so much of model is something which is not possible. So that's why we moved further and we tried to read inference rules. If you remember, we tried to see how an OR look, so that we can convert them into Boolean algebra, so that we can easily check it. Okay, so we moved to different inference rules. For example, we learned that we have a double negation elimination. If it is not true that Tyrion did not, it is not true that Tyrion did not pass the test. It's mean that he passed the test. So not times not. So not times not, which is A. Then we also moved further. I put on, because this is just a recap, I put on only few which are important. Implication elimination. If it is raining, then Tyrion is inside. So it means that if it is raining, he is inside. How I can read this in other words? It is raining or Tyrion is inside. So it means that this was implication. Like I said, that if left hand side is true, right is true. If it is raining, then Tyrion is inside. Mean if it is alpha, then beta is true. But I can say that either it is not raining or Tyrion is inside. So both of them are the same logic. So it means that I can convert this implication into if it is not raining or beta. So this is very important. Why? Because as I said that when you are trying to train in your AI agent, it's very important that you have known operators, because solving an R is easy to solve an implication, right? Okay. So it means that if we have A implies R, we will simply take not of A or beta. Similarly, then there was a biconditional error. So it says that it is raining if and only if Tyrion is inside. So this is bidirectional operator, which we already studied. So here we can say that if it is raining, then Tyrion is inside, and if Tyrion is inside, then it is raining. So we are covering from the both sides. So if he is inside, raining, or if it is raining, he is inside. So it means that here we have two implications. If it is raining, then Tyrion is inside, one implication, then an AND operator, then if Tyrion is inside, then it is two implications. So here you have, instead of two implications, I can say if A is true, B is true, if B is true, A is true, and both of them, right? So that's why it is very important that we convert this to the known form. Then we also came to know about De Morgan's law. We all know about it from Boolean algebra as well, that if you have a NOT operator on top of A and B, so if it is alpha and beta and you have a NOT, so you can remove the NOT, but this operator would be changed to OR. So this makes some sense. And similarly, if you have alpha or beta and you have a NOT overall, it would be alpha NOT and beta NOT. So NOT goes to either of them, and then the sign inside it is also changed. Then there is a distributive property. If you see that A and B are Y, so A and B then are inside A and gamma. And similarly, the distributive property over multiplication is if this is A or B, and then N would be inside and A or gamma. That's for gamma. Now, why actually we are trying to look for all these? Because we want to have, even in the previous case you can see that we wanted to infer something based on something, and that method was to have models and then check it. But here we'll do it in a slightly different way. Okay, now it's resolution. So Braun is in throne room, or Daenerys is in the library. So this was the information. Then it also gives us, tell us that Braun is not in the throne room. So it means that if he's not in the throne room, it means that Daenerys is in the library. So we can see that if I say this A or beta and not of A, then we can simply say it's beta. So you can see that we say P or Q, and if P is not true, now you can see that we are trying to, previously we only developed some logic, now we are trying to move towards the knowledge base, where we have a model and some more information about the model, so that we can make some resolution, so that we can infer something out of it. Okay, so here you can see that if P or Q, and if P is not true, you can simply say that these would cancel and you only have Q. And if I want to extend this, I can simply say that if P or Q, not of P or Q. In example, if P is in the room, Q is in the library, and R is in theater. So if we say that if he's not in the room, it means that either he's in the library or he's in the theater. So you can simply cancel it and you can extend it. So it means that you keep on extending. You just need to cancel these out and then keep on extending these things. So now in this case you can see that you have P. So these would cancel out. Then you would be having Q or S or R or S, and S is 2 times, so we will simply say that Q or S or R. So you can see that Q or S or R. So this we know that it was an empty clause where you have, if P is true and P is not true, it means that there is nothing happening. Now, it's very important that whatever information you have, you bring it to known form, which is called conjunctive normal form. In this form, you don't have any implication, you don't have bidirectional errors, you only have and you only have or, you have not, which is the known form. So it means that if you have any problem given, the very first thing would be to convert it into conjunctive normal form. And once you have that, then we will see that how we're going to make an entailment. So for example, I have this model, and if a new sentence came in, now you can see that in this case you have A, B, C, D, E, F, G. Now if you use the same method as we did before, it would be a huge 2 power 6 model, which is too difficult to check. So now we will turn toward that, how we're going to check the inference. Okay. So the very first thing is to convert to conjunctive normal form is, if you have any bidirectional arrows, convert them into single direction. Now we know that if A going bidirectional, if A is true, B is true, and if B is true, A is true. So you can see that this is the conversion from the bidirectional to single direction. And then the second thing would be to convert single directional into further knowledge, right? So we know that not of A or beta is the conversion of A implies B. And then if you have not outside or on the top, split it using the De Morgan's law. And if you have, lastly, if you have anything in terms of you need to apply distributive law just to open it. So it means that open everything that you need. So in this case, if I want to convert it, so what it would be? If I want to convert it into normal form, what it would be? So alpha implies beta. It was not of alpha or beta, right? So what it would be here?
P naught.
Consider this as alpha and consider this as beta, right? It doesn't matter if inside alpha you have further things, you will see with later, right? So it would be
P naught.
P, yes, P or Q naught or R, right? So whatever is here, you get a naught of it and then you will do an R. And now I know again I need to convert it further, so I will apply De Morgan's law. We'll take it inside, so it would be naught of P and naught of Q and
V R.
R, right? And then finally, what I can do, I can apply distributive law, right? So it would be P, I will put naught on top, P naught R, and then
Q.
and Q R, right? So this is how you will convert. If you have anything, you will convert it finally to a conjunctive normal form. Now, why it is important, you will see it in the next slide. So as we said that previously, for any information to check any new sentence with the knowledge base, we made a table and then we tried to check whether a certain sentence is entailing the knowledge base or not. But now we will do a different thing because checking model is slightly difficult. So here we will be using theorem proving technique. Okay, so just to remind you again, what is our main objective? Our main objective is to see if any sentence, whether it entails knowledge base or not. So that if our AI agent is trained, if it is going somewhere, and if certain scenario came in, then to see what to do, it has to refer to its knowledge base.
Cool.
What to do, right? So that's why it's very important that whatever comes in, you have to see whether it entails knowledge base or not. So here, to check whether it entails or not, sometimes in mathematics, if you cannot prove that A equals to B, it is sometimes more easy to prove that A is not equal to B. So if you prove a contradiction, if you prove something that, if for example, this can happen, and if you are unable to prove that in some way, you prove its contradiction and then you can say. So here, if we say that alpha entails knowledge base, so if we somehow prove that, if we take this condition that alpha doesn't belong to knowledge base, and if we somehow prove that this condition was wrong, if we prove a contradiction, so here we are saying that KB alpha doesn't belong to knowledge base. So if we somehow prove that this assumption or supposition was incorrect, then what is correct? Then it means that alpha entails knowledge base. So here, to prove that whether KB belong to knowledge base or not, we're going to prove that whether knowledge base and not of A is a contradiction. So it means that if we say that A doesn't belong to knowledge base, so if we prove this and that it is a contradiction, so if for example knowledge base was 1 and if we assume that not of A, so if alpha, if not of A is for example, if we say that this is 0, then ultimately you will see that it will get 1. But if for example, if alpha belongs to knowledge base, it would be 1, right? So it would be 1 times 0, so it would be 0. So it means that this is a contradiction, right? So it means that if alpha belongs to knowledge base, alpha, consider alpha is 1, it's true, right? If it is true, it means that this is contradiction. So now we're going to see that if we have any new sentence and if you want to see whether it entails knowledge base or not, don't need to draw all the models, just take the knowledge base and do an and with the not of this sentence. So if you find in the end that if it is a contradiction, then you will see that yes, it belongs to the knowledge base. So that's why, as I said, it is very important that to do such kind of operations, it's very important your knowledge base should be in conjunctive normal form. So if this is a contradiction, it means that alpha belongs to knowledge base. If no, then there is no entailment. So if this turns out as true, if this and is true for this case, it means that our new sentence is not entailing the knowledge base. So let's take an example. So as I explained already that to do that, the very first thing is to convert it to conjunctive normal form, and then try to see that if you have any new sentence, try to take not an and with the knowledge base, and it will tell you whether it entails or not. So here we are looking at that so this is your knowledge base, and we are saying does knowledge base entail entail A. So how to move with that? It means that this is the knowledge base and this is our alpha. So what we need to do? We need to take KB and alpha naught. We need to solve this. So get me the conjunctive normal form for knowledge base. Try to solve the conjunctive. So you need to take everything. So try to see if it is in conjunctive normal form or not. It is already in conjunctive normal form, right? Because there is no implication, there is no not on the top, everything is splitted like we want. So just try to take an end. So take knowledge base and take an end and solve it and tell me what you get in there. So you need to solve this one. So, you solve it. So here you can see that you have to solve this, and with B naught, and then you have to solve this. So you can try it later, but if I show you quickly is B and B naught would be cancelled,
Yes.
and you will be left with A.
Yep.
Similarly, C and C naught will be cancelled. So finally, if I say you will be left with A and A naught, and with A and A naught, you will finally get a
0.
empty clause. So it means that this is a contradiction. So it means that the output you get is 0. So it means that A index. And clearly we can see that in our knowledge base you were having an A. So if A is a new sentence, so roughly you can see that it should have it there. Okay. Now from here is something which is different. Okay, let's move on. So okay. Now if we extend, so far we are taking only few sentences and we were trying to do propositional logic, but we will see that propositional logic may not be very good if in case you have more variables in your structure. For example, here you have a logic puzzle which says that there are 4 people and each one belongs to one house. So John, Tyrion, O'Brien, Robert, and they belong to 4 houses. But then there is some more information about the problem. It says that O'Brien belongs to Stark or Martin. So it means that O'Brien can be one of them. Then it says Tyrion does not belong to Baratheon, and then finally says that John belongs to Stark. So it means that we have some information that we can use to draft our problem. So the very first thing is that if you want to look at the symbols, so these are the possible combinations. So 4 times John, 4 times house, because according to first statement, John can be in one of 4 houses. Similarly, Tyrion can be in one of 4 houses, and so on. Then if we move further, so we know that Tyrion does not belong in Baratheon, right? So one thing I can deduce here, if Tyrion is in Lannister, implies Tyrion is not in Baratheon, which is true. If this is true, this is always true. So this is some information we know. Similarly, we can draw it. If Tyrion is in, let's say, Ebron, then it cannot be in Baratheon, because one information that we know for sure is something that we can draw. Similarly, the second information is, we said that if Oberon can be in Martell or Stark, it can be in one. So if I said that if Oberon is in Martell, John cannot be in Martell, which is again true. So it means that here, if you look, you can draw infinite arguments out of it, because you have so many variables. And if I come to another one, we can say that if Ebron is in Stark, or Ebron is in Martell, based on this information. So it means that you can combine them to have so many sentences. So it is not very good logic to have only a propositional logic when you have more number of variables. So that's why it is very important that we go to first order logic. We will not go into more depth. We will just see that how a first order logic looks like. So in this case, again, if we go back to the propositional logic, you can see that you have so many symbols: John, Tyrion, then the houses, and so on. So it means that in case of first order logic, we tend to reduce the number of symbols. How are we going to do that? if you look from computer perspective, we'll see it in a while that we're going to make some functions which will make things easy. So we have two things. One are constant symbols and other we define as predictive symbols. So constant symbols are John, Tyrion, and the houses. These are the constant variables. Then we will see we have some predictive, in which case we'll see whether a variable is person or not. So this is our first function to check if I say Stark, so Stark is not a person. House, then we need to check which one is house, and then finally we'll make a function which will check that belongs to. It means that whether if this is a person, which house it belongs to. So it means that now you can see that our logic is a bit more concise, and we just need some functions first to check which one is person, and then to see whether it belongs to that house or not based on certain information. So if I say person is a function, so what it will give you, it will check whether something is a person or not. So person John, so it will say that John is a person, right? And at the same time, if I say house Stark, so it means that Stark is a house. And again, if you go towards the north, so not of house John, it means that John is not a house. And then belongs to, so first thing would be a person and second thing would be a house. So belongs to mean John belongs to Stark. And in the same thing, like I said, not, implications, everything would, all the same rules apply here. So if you go back to the same information, so how we going to write this first order logic? So here in this case, there is something that we know is for all x, and here we are using belongs to, right? So it means that for all x, so x is a person and second is a house, which we defined belongs to, right? So the first thing was person and second thing was house. For all x, that where x belongs to Stark, this implies that x doesn't belong to Lannister. So it means that here you can see that if Oberon only belongs to Stark, it cannot belong to Lannister. Why? Because one belongs to it at a time. How are we going to read it? For all objects x, if x belongs to Stark, then x does not belong to Lannister. So this is how we're going to define certain criteria. So this was a universal quantification, because this is something we definitely know about. That if anyone is belong to Stark, it cannot be Lannister. Because you can see that we have information on Stark and Martell, we have on Baratheon, we have on Stark, but the information that we don't have on Lannister. So that's why we chosen only Lannister here, because these are some definite information that we know, which is a universal quantification. Then we also have some existential quantification where a statement can be true for some cases. So for all x, where x is a house and John belongs to a certain house. So here there exists a house and object x such that x is a house and John belongs to that x. So it means it is true. X, there can be one x for which John belongs to. Then there is another thing. For all x, and if x is a person, there exists a y, and y is a house. So of course, if there is a person, for that there is a house, and x belongs to y. So it means that for all object x, if x is a person, then there exists an object y such that y is a house and x belongs to y. And we can combine whatever logical statement that we have studied previously, and we can use it as a first order logic. We will not go into more depth, We'll take a 5-minute break and then we will start another chapter which is probabilistic reasoning.
The new chapter, is it the new model? I mean, it's a new lecture, week 11.
Sorry?
The one you're gonna start, the week 11.
Yeah, it would be actually week 11.
Yeah, so how to display stop and I record the week 11. So